So let's do a little review of momentum. Most momentum conversations involve the conservation of momentum. Momentum itself is a vector, represented by a P with a line up top. Momentum is pointed in the same direction as velocity. Momentum is just the mass of an object times its velocity. Both of those are vector quantities. Mass is a scalar quantity. When we look down here and we just look, let's say, at a ball moving to the right with some initial velocity and it has a certain mass, so it's got a momentum. Not really a huge concern of ours. What we want to do is look to see how it interacts with other things. So we can make it hit a block, and we'll say that has some different mass, and that currently is at rest. And what we want to do with momentum is really talk about the conservation of momentum. Again, this has momentum, this has no current momentum, and then they're going to have some collision. And in the collision, we're going to talk about the conservation of the system's angular momentum. So most of these involve looking at not an object's momentum, but the overall system momentum. And realistically, what we want to do is look back over here and look at F equals ma. We are very comfortable with how the net force on an object will cause the object to experience a certain acceleration. Well, in momentum, we often talk about an external force. And if in the absence of no external forces, then we can't have any accelerations, which means we can't change our velocity, which means we can't change our momentum. All that is saying is that eventually the change in momentum will equal the accumulation of some net force over time. Again, the net force is likely going to be a function of time. If it wasn't, then algebraically we can just say it's some F times delta T if the force never changes, meaning the force times the time will equal the change in momentum. Well, think about this. This isn't any different than just saying the mass times the acceleration times t. But think about what at just represents the velocity. The velocity, well, the change in velocity, times the mass. Of course, it equals the change in momentum because momentum is mass times velocity. Again, most of the time we're looking at conservation of momentum. We conserve momentum when the external force is equal to 0. That means that there's no change in momentum for the system. I didn't mean to imply that there's no change in momentum for an object. When this ball hits this block, whether the ball bounces off, whether the ball sticks, whether it's complete, whether it's elastic, it doesn't matter. Each one of them are going to experience a change in momentum. Each one of them individually have a force applied over a certain time period, which will cause a change in momentum. But the system in general, and really, that's Newton's third law. The system in a collision, when you think collision, you have to think about Newton's third law. The ball hits the block, but the block hits back the ball. There's no external force to the system, which means there's no change in momentum to the system, which means that the momentum at the beginning, and this is our classic statement, the momentum at the beginning equals the momentum at the end. And again, this is true, conservation momentum, when there's no external force. No external force to the system means no change in momentum, and no change in momentum means whatever there was at the beginning, there is at the end. In general, this is the overview. We actually do give this a special name, which I'm sure I'll talk about later. We talk about the impulse. And again, objects can have impulses. Systems can even have impulses. But if a system has an impulse, it's because there is an external force. Without an external force, there's no change in momentum. Okay, let's talk about the recoil of a gun or a cannon. So this is some cannon that has some capital M mass, and then we have some cannonball with little m, and we're going to shoot the cannonball. And so what we're going to do is we're going to experience recoil. Recoil will be like firing a gun this way, and then having you go that way. It's the gun, hitting your shoulder and pushing you backwards. In movies, this is really hilarious because there's a person in a movie, the good guy, of course, fires a bullet this way, boom, and it hits the bad guy. And the bad guy gets hit by the bullet and totally falls over to the ground. And yet the good guy felt no effect of shooting the bullet. That is classic bad movie physics. If the bullet had enough momentum to make this person fly into the wall or fly to the ground, then it would have the same momentum to shove the good guy back this way. Again, don't look at movies in terms of what would happen in terms of firing something. Every now and then, if you watch a pirate movie, then we're going to look at a cannon, and they have a decent amount of recoil. In this, we would say, again, there's no external force. Whatever force the cannon applies to the bullet applies to the cannon, and we would say something like this, where the beginning momentum, well, nothing is moving in the system, so none of them have any momentum, and in the end, we'll call the right positive, and so the bullet gets this m v naught, and then the cannon would have to get some other, we'll call that maybe v2. Again, if you shoot a bullet to the right with mv naught, you're giving it positive momentum to the right. Well, whatever that force is, there's an equal and opposite reaction backwards. In terms of momentum, it has to be the same, because this net momentum can't be anything, because there was no external force to the system. This is an explosion. When you think explosion, it's the same thing as a collision. And then if we knew these values, we could find the v2, we could find the recoil velocity of the cannon if we knew the cannonball's mass, the cannonball's velocity, and the cannon's mass. Mainly there's three, I shouldn't say mainly, there are just three types of collisions: elastic, inelastic, and completely inelastic, or sometimes they'll say perfectly inelastic. All elastic collisions, what that means is that no energy is lost. What that would claim is that there's no heat produced or anything else where we would lose to the environment. Okay, and that's, an example. If you took a bouncy ball and you dropped it, if it was a completely elastic collision with the ground, the ball would go right back up to its height. No energy is lost. Now we know that doesn't actually happen. Same thing here. If I took a ball and I threw it horizontally at another ball and they bounced off of each other, if we looked at the total energy of before and afterwards, if you could show me that E1 equals E2, I guarantee that it must have been elastic, right? That's the definition of elastic. Inelastic, well, that's just our classic collision. Probably, 95% of all collisions are just inelastic. And that's just where they glance off each other, they bounce off each other, and energy is lost. Usually, a lot of energy is lost. Not like 5% of energy, but sometimes like 90% of energy, or 80% of the energy is gone. It doesn't all transfer. Momentum, all three of these, it doesn't matter what type of collision it is, the momentum is conserved. Conserve momentum. Again, because in any of these cases, there's no external force. There's no external force. The momentum at the beginning is the momentum at the end. No big deal. So we can say P1 equals P2 or PI equals PF for all of these things. And then the words completely inelastic or perfectly inelastic, that just implies that they stick together. And if they stick together, it would be a situation where, let's say we have this situation up here. We'd have, we'll go P1 equals P2. And at the beginning, it's M1 V naught is the only thing that has the momentum. And if they stick together, well, if they stick together, they're moving at the same velocity. So you can treat them as the same object. And you would write something like this. If they didn't stick together, you'd say something like M1 V naught equals M1 V1 plus M2 V2. They both have their own individual momentums. Maybe when it hits the result, they're both going this way afterwards. So these two would both be positive quantities, and you'd figure that out because when you did the math, both V1 and V2 would end up positive. Maybe M1 rebounded this way. Well, when you do these calculations, you better get a negative V1 for this because it would have a negative momentum. Again, you don't have to put a minus sign or a plus sign. You will get a negative or a positive for V1 or V2 based on which of these they did. And how you know it did this? Well, it's going to be all based on the mass. Okay? Elastic, well, elastic has their own special equations, which we'll talk about in a future thing. Not necessarily something you want to memorize, but in elastic, what we're going to do is we're going to derive P1 is equal to P2, and we know that E1 equals to E2, and we can actually get a result from that. All right, let's revisit impulse. When they say impulse, we're talking about the change in momentum. They might talk about the units would be Newton seconds, but it's just the change in momentum. Momentum is a mass times the velocity, so it's really a kilogram meter second. Those are the same units. This makes more sense because it implies what's happening. You're applying a force for a certain amount of time. So if I give you an impulse, let's say, and I give you a 40 Newton second impulse, that could be me giving you 40 newtons of force for 1 second, or obviously we can do this as many times as we want. 20 newtons of force for 2 seconds. That's a 40 Newton second impulse. That means I've changed momentum by 40. That's not a change in velocity, it's a change in momentum. But if you knew an object's impulse, then you could find the change in velocity. I mean, if the mass was 10 kilograms, and you gave it an impulse of 40, then you'd have a change in velocity of 4 meters per second. So whatever the velocity was, it just increased by 4. Again, assuming the impulse was positive, which means to the right. Again, if the force is constant, then we don't really need calculus, because we can just take a constant force times the time it was applied to give you this. Basically what we did down here. If the force is not constant, so the force is some, it can be a trapezoid, it can be whatever we want, let's say it's some decaying force now. We can't just take the force times time because the force changes as the interval increases. And so what we really have to do is find the area under the curve. It's a concept we've viewed before. We have to accumulate this force over really small intervals of time. We're breaking this thing up into really small rectangles. And that's what an integral actually does. And so when you find this, the area under this particular curve is equal to the change in momentum, which is the impulse. And again, once you find the change in momentum, then divide by the mass to actually find the change in velocity. You can find the effect of that impulse. But you'll do a decent amount of graph questions. As a reminder, F versus X. This is not momentum. This was work. So recall the energy unit. If you apply a force over a distance, you do work. If you apply a force over a time period, you get a change in momentum. Okay? So just make sure we keep track of that. Calculus-wise, this, and we could say that the force is dp dt, just doing that in reverse. If we look at the rate at which we change our momentum is force, well, of course it is. Look at momentum. Momentum is mv. And what's the derivative of both sides? Well, if I take the derivative on this side with respect to t, and I take the derivative on this side with respect to t, dv dt, well, that's just a. So we just decided that dp dt, the rate at which you're changing momentum, is ma. Well, that just means that that's force. Of course it is. It's the reverse of those. So we have, I think, one problem left, the ballistic pendulum problem. We could do more. I mean, there's explosions instead of collisions, but really they're all the same thing. Maybe we'll do an explosion after the ballistic pendulum. The ballistic pendulum is taking a bullet of mass little m with V naught and firing it into this block. And typically, it lodges in. So let's first look at what happens if it sticks. All right, if it sticks in the block or gets lodged in the block, both of those things are going to swing up. So they're going to swing up, and then they're way up here. And there's really two phases here. Phase one is all about momentum, and momentum is all about the collision. Because during the collision, momentum is conserved. Energy is not conserved in the collision. Tons of heat is going to be produced and lost in the environment. But momentum is conserved because there's no external force. Okay, so the momentum at the beginning is like an m v naught. The hanging thing, the hanging block doesn't have any momentum, so it doesn't contribute. And then afterwards, if they stick, well, we can say then the total mass is going to travel at some vf. And so if you tell me the masses and the velocity, I'll tell you how fast it's moving. Afterwards, now it's all about energy. And when I say it's all about energy, now we're talking not about the collision, but we're talking about the swing. So the objects are already lodged in, and it has a certain velocity, vf, and at that point it's got all this kinetic energy, and it's going to fly up, and eventually it's going to stop. So at the beginning, when I say it, I mean the system, little m plus big M, and I'm going to put vf squared because this vf, I know it's really a v naught in this situation, but it's this vf. All that kinetic energy is going to be transferred to potential energy. And again, we have to look at the height. But if this is our swing, up to there. This is this height. And again, go through the whole thing. If this is the string length L and this is theta, then this length from here to here is L cosine theta. The total length is L, and so the difference, meaning the height, that height change, is L minus L cosine theta. And again, you did that a decent amount of energy. So that's the value you can put there. And then you can actually, if you tell me this information, I can tell you how fast it's moving, which I can then tell you how much energy it has, and then I can tell you how high it's going to swing, which then I can convert to figuring out what angle it will make with the vertical. If it doesn't stick, so maybe the bullet passes through, let's say that you fire the bullet, it passes through the block and decreases its speed by half. You're still going to conserve momentum. You're going to say this is some mv naught, and if it passes through and is still going, so it has that momentum, and then vf. You still can use this equation to find vf. You can still use this, oh buddy, look at this over here, this m. That was really supposed to be m plus big M, right? That was the mass of the system. My bad on that. Make sure you make that correction. But this, going back over here, if it passes through and let's say decreases its speed by half, it still has momentum, so it transferred less. This VF will be smaller than that VF. That's okay. When you get this VF, then it's got energy, and in this case, you're just looking at the big mass and having the big mass still swing up to some height as the bullet passes through. So it doesn't have to stick, but most of the ballistic pendulums stick. Let's look at one more. Let's look at an explosion. And so sometimes they talk about multiple fragments. And again, just remind you, if we do the recoil problem, and it's some cannon, and it's some cannonball, and the cannonball goes this way, and that goes that way. I mean, I know we think of this as actually something shot, but it's no different than an explosion. An explosion, a collision, explosion, are all the same thing. No external force, no change in momentum. And so lots of times we have this, let's say we have this object and it's sitting and it's stationary. And then what's going to happen, it's going to have a grenade in, it's going to explode. And then we're going to have like one fragment go that way, one fragment go this way, and one fragment go, oh, something like that. And they're all going to have different masses, those pieces, and they're all going to have different velocities afterwards. Okay, we'll call this one theta 1. We'll call that one theta 2, and we'll say that M2 actually goes straight to the right. And realistically, we're just going to conserve momentum. We just have to do it in component form. So for the x direction, this is positive, so M2 V2 plus M1 V1 cosine theta 1. Right? It's the horizontal component of momentum that way, plus this momentum, and then minus M3 V3 cosine theta 3. And we know that it's equal to 0. We know it's equal to 0 because there's no initial momentum. Really, we're just saying Pi equals Pf all over again. We just are doing it in components. And vertically, the same thing. This has a vertical. M1 V1 sine theta 1 is up. This is an up or down, and then minus M3 V3 sine theta 3, and it also equals 0. If there's no original momentum, then there can't be any final momentum. Again, I didn't say each piece couldn't have momentums, but each piece all added together, when taken into account, they all have to be the same. So this right and this right momentum has to cancel with this left momentum. That's what this statement is saying, because we know there's no original horizontal momentum. If this up has to equal this down, up equals the down, right? Subtracting them equal to 0 is the same thing as setting them to each other. Okay? This problem doesn't change anything. What if I said that the box was actually moving this way with some v equals 4 meters per second at the beginning, and then the explosion happened while it was moving? Okay. Still didn't have any vertical momentum, and you'd go up here and you'd say, okay, this is just M1 plus M2 plus M3 times 4. That's the momentum it had horizontally, so that's still the momentum. it has to have horizontally. That's not going to change. Again, it doesn't matter. This messy writing over here, again, that's just the total mass. That was m1 plus m2 plus m3 would be the original horizontal momentum, which equals the final horizontal momentum. Vertically, if it was sliding to the right, it still didn't have anything, so vertically afterwards, it still can't have anything. Again, if there's no external force, there can't be a change in momentum. An explosion, a gun recoil, a collision, all of those are just internal forces, and Newton's third law really justifies all that. I hope this helped take a looking at momentum, but again, most of the time you're thinking about a collision or an explosion, conserve momentum, and then after that, once you find out velocities of pieces, well then maybe you're looking at energy or forces to calculate other things, but momentum is probably your go-to move if you have a collision or an explosion.